Welcome to the Explainer. Today we're unlocking a superpower. Seriously, it's one we all use every day but probably don't even think about. The ability to command light, letting us see way, way beyond the limits of our own eyes.
You know, our world is just packed with things that are either too tiny or too far away for us to see. So how did we ever build the tools to peek into those worlds? Well, it all comes down to understanding two fundamental keys, two ways we can control light itself.
Okay, so the first and honestly the simplest way we manipulate light is just by bouncing it. It's called reflection, and it's all governed by this one beautifully elegant rule. The angle that light hits a surface is the exact same angle it bounces off. That's it. Simple, right?
Now here's where we start to play some amazing tricks. If we curve that reflective surface, we can do some cool stuff. Curve it inward, that's a concave mirror, and suddenly all those parallel light rays get focused to a single point, magnifying whatever we're looking at. But if you curve it outward, making a convex mirror, those same rays spread apart, giving us this huge wide-angle view.
And believe it or not, this one little equation is basically the secret recipe for all of it. It's like a blueprint that lets us predict exactly where an image is going to show up, how big it'll be, everything you need to know for any curved mirror. So that brings us to our second key, which is honestly even more powerful. It's called refraction. Now, we're not talking about bouncing light anymore. We're talking about bending it. Refraction is what happens when light changes direction as it goes from one material, like the air, into a different one, like water or a piece of glass.
And this elegant little law here is our guide. It tells us that when light enters a denser material, say from air into glass, it actually slows down and bends. It bends toward this imaginary line we call the normal, and the higher that n value, the refractive index, the more dramatically the light bends.
But this is where things get really cool. Instead of bending toward that normal line, when light tries to escape a dense material, it bends away from it. And if you keep increasing the angle it's trying to escape at, something absolutely incredible happens. This one property is literally what powers our modern world.
Eventually, you hit this tipping point. It's called the critical angle. At this one precise angle, the light ray trying to escape doesn't really get out. It just skims perfectly along the surface of the water. So, any angle smaller than that, and the light gets out. But what do you think happens if we make the angle just a little bit bigger?
And boom, we get total internal reflection. The moment the angle of incidence goes past that critical point, the light just can't escape. It's physically impossible for it to refract. The boundary between the water and the air suddenly turns into a perfect mirror, and 100% of that light gets reflected right back into the water. It's trapped.
And this whole phenomenon of trapping light is not just some neat physics trick. It is the fundamental core principle that makes optical fibers work, the very fibers that carry the data for our entire global internet. So, now we have our two keys, right? Reflection, which is the art of bouncing light, and refraction, the art of bending it. So let's see how we combine them to build the incredible instruments that have totally unlocked new worlds for us.
Okay, so to see something super small, we use a compound microscope. It's a clever two-step process. The first lens, the objective, it creates a magnified, real image of a tiny object. Then, the second lens, the eyepiece, takes that first image and acts like a powerful magnifying glass to blow it up even more.
Now, to see things that are really far away, we use a telescope. It might look similar, but its goal is totally different. That big lens on the front, the objective, its main job isn't just to magnify. Its job is to be a giant light bucket, to gather as much faint, ancient light as it can from a distant star or galaxy. It focuses all that light into a small, bright image that the eyepiece can then magnify for us.
So yeah, even though they both use a two-lens system based on refraction, you can see their designs are pretty much polar opposites. The microscope is built with short focal lengths to see things that are incredibly close. The telescope, on the other hand, uses a long focal length and a huge opening to see things that are incredibly far.
But let's circle back to that incredible idea of trapping light with total internal reflection, because this is the foundation for one of the most important pieces of technology we've ever invented, the optical fiber.
Okay, so an optical fiber is basically a light tunnel. It has this inner core of unbelievably pure glass, and it's surrounded by an outer layer called the cladding. And here's the secret. The cladding has a slightly lower refractive index than the core. That difference is everything. We shoot light into the core at a really sharp angle, which guarantees it always hits that boundary at an angle greater than the critical angle. And so, it gets trapped inside.
And this whole process is just astoundingly efficient. A modern optical fiber can guide a pulse of light for a full kilometer and lose less than 5% of its intensity. The light literally bounces millions of times, even around corners, carrying our data at, well, at the speed of light.
So think about it. We started with a simple rule about how light bounces off a mirror, and we ended with a clever trick for trapping light inside a tiny thread of glass. In doing so, we've basically given ourselves a superpower. We've built these new eyes to see the universe on every possible scale, and that has fundamentally changed what it means to observe anything. The only question left is, what new windows will these same principles help us open up next?